All right, we're going to continue to review differential equations. And this is sort of the overview that we talked about. On the very first lecture, we went through and talked about what causes differential equations in dynamic systems. And we said it was the result of energy storage elements in the system. Then we went through and talked about how to solve first order differential equations. And then last time we talked about second order differential equations. And we will start to talk about numeric solutions as well. This portion of the lecture, I'm going to look at an example second order. All right, so just to remember, what we've talked about in the past, we've talked about this idea of what we call non-homogeneous differential equations with constant coefficients. And what that means, this term non-homogeneous refers to the fact that there is some input over here, x of t. All right, and somehow this is a model of some physical system. I could get it from KCL and KVL if I had a circuit, for instance. Or I can get it from Newton's law or something if I had a mechanical system. So this x of t is our input, sometimes called the driving function or driving force. It's what makes something happen in this system. We call it non-homogeneous, of course, because it has that x of t. If there isn't an x of t over here, we call it a homogeneous differential equation. And we deal only with constant coefficients, okay? All right, and this is our general form. And we said we dealt with a couple of different types of inputs, all right? We said we were going to deal with step inputs, exponential inputs, and sinusoidal inputs. All right, now typically, we apply all of our inputs at time t equal to 0. We don't have to, but we typically do. All right, and so we defined this idea of the unit step, which is shown here. All right, this guy up here is our unit step. What we see is at time t equal to 0, this guy goes from being equal to 0 to being equal to 1. Okay, so mathematically we define this as 1 for t greater than or equal to 0 and 0 otherwise. All right, and we say t greater than or equal to 0. All right, that should be greater than or equal to. And we said this sort of represents if I had a circuit like what I have shown at the bottom, right? If I did KVL here after the switch, okay, what I would, if I measured, let's say I put my oscilloscope probes across the circuit where I've drawn the plus and minus there after the switch. Before the switch closes, if the switch closes at t equal to 0, before the switch closes, I would measure 0 volts. After the switch closes, I would measure 1. All right, so this models the closing of a switch. So if I applied, let's say, a cosine as my input to the system at t equal to 0, then I would multiply that cosine by u of t. All right, now we'll see how we do that, right? How we use it. We don't usually keep the u of t around in our analysis. We basically just solve things specifically for t less than 0 and t greater than or equal to 0, okay? Now, a key thing to remember here is the steady state output, what we call YP, the particular solution, always looks like the input x of t. All right, so I've got that summarized here. If I have a constant input applied at t equal to 0, and notice I said a times u of t. So that means that I could take a u of t, right, would basically be this unit step multiplied by a constant. So if my input was 2 times u of t, then I basically would take u of t and multiply it by 2, okay? If I have a constant input, I will get a constant output. If I have an exponential input, I'll have an exponential output. If I have a cosine input, I'll have a cosine output. Notice that in the case of the cosine, maybe the amplitude's different and the phase is different, okay? All right, so we'll have to remember that, all right? In the case of the cosine, notice that the frequency will never change though. If the frequency of my input is omega, frequency of the output's gonna be omega. All right, the input and the output always look the same in steady state, okay? All right, so last time we talked about second order differential equations, all right? Y of t is the output of our system, all right? So this could be, either an inductor current or capacitor voltage in the circuit, okay? So it's important to remember that the output always corresponds to one of the energy storage variables, either the inductor current or the capacitor voltage. Never a inductor voltage or a capacitor current. Okay, that's important to remember. So we can always get that equation in this form. All right, there could be a term A here, let's say on that first term, but I'm not going to include it because it's not standard to do so, right? You could just factor this a little bit to get rid of that and make this term equal to 1, right? If I had put A here, then I could have divided both sides of the equation by A and gotten it into this form. All right, but there could be. All right, that doesn't really change the process at all, right? I'll follow a similar process if I do that. Okay. Now, in general, our solution has the form yp of t plus yc of t, where we said yp of t is the steady state solution that solves the particular equation, and y sub c of t is the characteristic, or sorry, the complementary solution or transient solution that solves the homogeneous equation. Okay, so our solution approach we've talked about a couple of times now, and in this lecture we're going to build out, particularly for second order systems, a more complete approach for step 3. All right, but essentially what we have is we solve the homogeneous equation. This gives us the homogeneous transient or complementary solution, which I always call y sub c to be consistent with the book. And then we solve the non-homogeneous equation. That gives us the particular solution or the steady state solution. And we use what I called the undetermined coefficients method, which is to say, if I know what the input looks like, let's say it's a constant, I know that the output is a constant, but I don't know what this coefficient is. So I have an undetermined coefficient whose value I need to determine. Okay? We call this steady state output y sub p. The total solution puts these two guys together, and I used my initial condition to solve for any remaining constants. Okay. Now we know that we're talking about a second order system. And so one of the things we said is if I have a second order system, back up for a second, I guess in any system, our transient response contains exponentials. If I have a second order system, that means that it includes 2 exponentials. Okay. So we're gonna go through that process here a little bit today, but that's one important thing to remember is that my transient response always contains as many exponentials as the order of the equation. Okay, and so that means we're always going to have 2 exponentials in this case. All right, so let's go through the transient solution. And just kind of remember what that looks like here. All right, so what we do is we always say we write down the homogeneous equation, meaning we take the output out. We guess y sub c of t to have this form, c e to the st, where we know c can't be equal to 0. We plug that into this equation, meaning we have d squared by dt squared of c e to the st plus d by dt of c e to the st plus c e to the st, all equal to 0. Now, one thing we know is c can't ever be 0, and e to the st is never 0. All right, that's an important thing to remember. Take the second derivative here, and this becomes s squared c e to the st plus s c e to the st plus c e to the st equal to 0. Second derivative brings down an s squared over here, right? The first derivative brings down an s. One thing I notice is I have a c e to the st in each term, and I get s squared plus, and I got to be careful. I left a couple of things out here, right? I left out my coefficients, right? There was supposed to be a b in front of this guy, and it's supposed to be a little c in front of this guy. Okay, so like this. Probably should choose little c and big C, but I have that. All right. I see that I have big C e to the st in each term, so I can factor it out. That's what I was doing. And I get that result. Okay. So because c is never equal to 0 and e to the st is never equal to 0, I'm always left with this thing that I call the characteristic equation that must be equal to 0. And I can solve that using the quadratic formula. Now, we talked about this last time. All right, this thing is called the characteristic equation. You can solve it with the quadratic formula. You should be able to figure out where this formula came from. All right, this will always have two roots. So there are always two terms in the transient response, okay? Always two exponentials. That means I'm going to have this form. So notice I said C1 is the unknown coefficient that goes with the S1 term, and C2 is the unknown coefficient that goes with the S2 term. All right, C1 and S1 go together, C2 and S2 go together. All right, now the exact form of these terms depends on the nature of the roots. All right, so it's possible that S1 and S2 are complex. All right, it's also possible that they're purely real. All right, so basically here's a summary. We went through this last time. We basically have 4 different cases that we would talk about. If we had an ideal system where we had a purely sinusoidal output, in that particular case, we get that our roots, so if there's no losses in the system, right? We say we had a purely sinusoidal output. No losses ultimately mean that the B term is equal to 0. And I get 2 roots that are entirely imaginary. If those 2 roots were entirely imaginary, I'm going to end up with that expression using Euler's identity. And we'll see an example of that later. If I have an underdamped system, meaning I had some loss, that gives me a decaying exponential. That's what I have here. All right, decaying exponential. So you notice I have I should say a decaying sinusoid. Okay. If you look at this, right, I have a cosine term multiplied by e to the sigma t, but that sigma is the real part of the root. That real part's always going to be negative, which is going to make the amplitude of this cosine always decrease. Now, the other 2 cases, the roots are real. Critically damped, they are real and the same. Notice that those are the same 2 values. Now, you can go back for the uniqueness theorem in differential equations. You should have learned the uniqueness theorem. Well, one thing we can do is we can create essentially 2 linearly independent solutions. In this case, we can't have e to the S1t and e to the S2t. That wouldn't work because those are not 2 unique solutions. We multiply by t to make that work. I'm not going to focus on that too much. I'm really not going to focus on that at all because it doesn't really happen very often in real systems. Okay? All right, so we have for critically damped C1 e to the S1t plus t C2 e to the S2t. By multiplying by t, I get 2 solutions here that we call linearly independent. All right, and I'm not going to focus on that too much. For overdamped, I have the same result that I have for underdamped and undamped. All right, except the roots are real and distinct. Okay, meaning that they are different. Okay, all right, so a couple of important things, okay, to keep in mind. For the undamped and underdamped case, C1 and C2 are always complex conjugates. S1 and S2 are always complex conjugates, okay? All right, and you see that in the way I've written this here, right? Sigma plus j omega d, sigma minus j omega d. That's what leads to the fact that these exponentials become a cosine, all right? Now, for any real system, the real part of the roots must always be negative. All right, that's important. If they weren't negative, that would mean that these results would be exploding. In other words, they would be getting bigger over time, which means that the energy stored in the system would be getting bigger over time, and the universe doesn't allow that. All right, so if you get positive real roots ever, you've done something wrong. Okay, go back and look at what you did. All right, so we're going to look at an example here. All right, so I've got this equation. All right, so I've got a second order system that is equal to some sort of a cosine that is applied at time u of t, and we're given 2 initial conditions here. All right, we have to be given 2 initial conditions because we ultimately have 2 unknown coefficients that are going to come out of this. So we're given an initial condition on the y of 0 and we're given an initial condition on the first derivative of y, okay? All right, so let's go through this process. The first thing we got to do is we got to solve for the transient response. So let's do that. This transient response solves what we call the homogeneous equation, which means we take the input out, and we have d squared yc dt squared plus, what was it, 4 dyc by dt plus 3yc equals 0, okay? Now, what we do, we said we guess y sub c of t equal to c e to the st with c not equal to 0. And ultimately, we said that we plug that in there, and that's going to lead to s squared plus 4s plus 3 times c e to the st equal to 0. But because we know c is not equal to 0, we know e to the st is never 0, we get our characteristic equation, s squared plus 4s plus 3, which tells me that one I don't even need to take into the quadratic formula, because I can factor that one, old school, and say it's got to be s plus 3 times s plus 1, right? So that tells me my roots here are s equal to minus 3 and s equal to minus 1. All right, notice that they're negative, exactly like what I would have said they would have been. All right, we said, oh, my roots always have to be negative. That means I'm going to have exponentials that decay. So that means that ultimately I have, let me say, I just want to be consistent with my solution later. Okay, I have y sub c of t equals c1 e to the negative 3t plus c2 e to the negative t. All right, and it's really only for t greater than or equal to 0, right? Because we didn't apply our input until that time. Okay, so that's our result. Now, we don't know enough yet to compute C1 and C2. That we can't do until the very end of the problem, okay? So we're going to do that at the end of the problem. All right, now time for the particular solution. As we said, particular solution always has the same form as the input. And in this case, x of t was equal to 4 cosine omega t plus 45 degrees. And I guess specifically the omega in this case is 10. So 10t plus 45 degrees. Okay, you can flip back in the notes to see that. All right, so that means that my input looks something like this. Now, again, I don't have an RC circuit in this case because I got a second order system, but you should get the idea. What I'm focused on is basically the input to the system, which is, say, this voltage source here, okay? Now, these two circuits here are equivalent, all right? Let's say I was solving for this capacitor voltage. This would be y sub, if I'm talking about the steady state, I'm talking about y sub p, right? These two circuits here are entirely equivalent, all right? What I've done, instead of writing a cosine omega t plus phi x over here, I have written that as the real part of a e to the j phi x times e to the j omega t. You should be able to see the clear relationship between those two things. Now, in this particular case, y sub p is the real part of b e to the j phi e to the j omega t. This case, it would have been b cosine omega t plus phi. So as we said, right, the form of the output in steady state better look like the input, okay? And so the same is true in this circuit over here, all right? So we have real part and real part. Now what we said is, since I just take the real part, so if my input is the real part of some phasor, some dynamic phasor, then my output is the real part of some dynamic phasor. What we've said is we do all of our analysis here in the phasor domain and solve for the dynamic phasor I would have here, and then essentially take the real part at the end, okay? So our process then basically is to say we have a yp that we guess that is the real part of b e to the j phi e to the j omega t. Do all of our analysis in the phasor domain, meaning just forget the whole real part thing and basically just do the analysis on this, and then take the real part of the result. Okay, so let's guess yp equal to b e to the j phi e to the j omega t. Now I'm going to keep it as omega because I want to parameterize my stuff in code. I like to do that. All right, I'm just going to say my omega is 10. All right, so we're going to take the whole circuit over to the phasor domain, or take the whole system there. So I'm going to say at d squared yp dt squared plus 4 dyp by dt plus 3 yp equals 10. So remember our input was not 10. Our input was 4 cosine 10t plus 45 degrees. Let me just make sure that's really what I had. Okay, yeah, 4 cosine 10t plus 45 degrees. So I'm going to write this as 4 e to the j 45 degrees times e to the j omega t. And I'm going to leave it as omega again. Omega is equal to 10. I'm just going to leave it that way. All right. What I want to do is I want to plug yp into this expression. So I get d squared by dt squared of b e to the j phi e to the j omega t plus 4d by dt of b e to the j phi e to the j omega t plus 3 times yp, so that's b e to the j phi e to the j omega t. That's equal to 4 e to the j 45 degrees times e to the j omega t. So I've got an e to the j omega t everywhere, okay? So I take the second derivative. Now the only terms over here that have t are the e to the j omega t terms, right? So those are the only terms I can take the derivative of. If I take the second derivative here, I'm going to get j omega to come down 2 times. So I have j omega squared times b e to the j phi e to the j omega t plus, again, now I get a first derivative. So in this case, I would have 4 times j omega times b e to the j phi e to the j omega t plus 3 b e to the j phi e to the j omega t equals 4 e to the j 45 degrees e to the j omega t. All right, so e to the j omega t is everywhere. All time dependence is lost. Okay, and that's great. That allows us to do impedance analysis, which is what you're learning in circuits 2. All right, now let's simplify this guy down here. Here I have a j omega squared. If you do a j squared, all right, that is square root of minus 1 times square root of minus 1. All right, so if I have that, you should see that that becomes minus 1. All right, I just have, I guess the easiest way to see that, I think, there's a couple of ways to do that. There's a couple of ways to see that. I think the easiest way might be to say if I have minus 1 to the half times minus 1 to the half, right? If I multiply those two guys like that, right, that's just going to become minus 1/2, right? So minus 1 to the half times minus 1 to the half, you add those two exponents together, right? And I get minus 1 to the 1, okay? All right, so that should make some sense. So let's simplify this guy down here then. It looks like I have on this side minus omega squared, that's how this guy is simplified, plus 4j omega, okay, plus 3 times b e to the j phi 4 e to the j 45 degrees, okay? That is an expression there that has essentially one equation, but two elements, right? There's an element for the angle and there's an element for the magnitude. So I wanted to take that over here and do that a little bit more slowly, just so everybody sees it, right? I'm gonna rewrite it like this: b e to the j phi equals, right, 4e to the j 45. So 4e to the j 45 degrees divided by the stuff that I had on the left side before, this term here. So I'm going to write this as 3 minus omega squared plus j times omega times 4, like that. Okay? All right. Now I left it in terms of omega. Remember that our omega is equal to 10. I'm going to write my code that way, just define it that way. So when I look at it like this, what I see is I've got two expressions here. If I took the magnitude of both sides, all right, that would be over here on the right side, magnitude of the top divided by magnitude of the bottom. And over here, the magnitude of b times the magnitude of e to the j phi. Talked about this before. Magnitude of the e to the j phi is always 1. So that means that b, and again, if this was a coefficient on a sine wave, okay, b would just be a real number, right? So I don't need to worry about saying magnitude of b. It's always going to be a real number, all right? So the magnitude of 4e to the j 45 is 4, right? Because e to the j 45 degrees has a magnitude of 1. And on the bottom, I have square root of 4 omega squared, that's the imaginary part squared, plus the real part squared, which is 3 minus omega squared quantity squared, okay? That's what I get when I do the magnitude. Now what I want to do is I want to do also the angle of both sides, okay? So the angle of both sides. So when I take the angle of both sides, like that, okay? The angle of the left side here is pretty easy because, again, we said b is always going to be, since it's the amplitude on a cosine function, it's always going to be a real number. So it's going to have no angle. So e to the j phi has an angle phi, and that has to be the angle of the top minus the angle of the bottom. So the angle of the top is 45 degrees in this case, and I'm simply going to say angle of the bottom like this: 3 minus omega squared plus j 4 omega, like that. Reason I'm saying that is because I think what's going to happen here, if you plug in omega equal to 10, you're going to see that my real part is negative. And if I have a negative real part, right, if we think about our quadrant, I'm going to have a negative real part and a positive imaginary part. So it's going to put me somewhere over here in the second quadrant for that vector on the bottom. Okay. That means I can't just use arctangent. All right. I did that on purpose. I used a little bit of my intuition here to state that, because I knew that was going to happen. All right. Now to solve this, what I do is I do this in MATLAB. All right. So what I did here is I got a little piece of code where, okay, so I use this roots function. I talked about that. The roots function will solve for me the quadratic equation. So if I had my characteristic equation is s squared plus 4s plus 3, like that, right? And that's equal to 0. What I did was I said I can take the coefficient and put that as the first element in a row vector, this middle coefficient, and make it the second, and make this the last one, okay? And I take the roots of that, all right? So that basically says get the roots of this polynomial, which are -3 and -1. And then, like I said, to get the b and the phi values, what I did here was I defined omega equal to 10, and then here, if you look, this is b e to the j phi equal to 4 e to the j 45 It's exactly what I had on the previous slide, right? So on the bottom, I have 3 minus omega squared plus 4j omega, like that. All right, and you see what I've done here is I've just said, instead of b e to the j phi like that, I've defined this as some variable b complex, all right, which has a magnitude of b and an angle of phi. All right, so what I did was I basically wrote this expression in for b complex, and then I took its magnitude using the abs command, and then I took its angle using the angle command, which is going to give me something in radians. I don't like radians, so I multiply by 180 over pi. So what I see here is that my b value is written out, my phi value is written out. So that means that my yp of t is the real part of, remember, it's the real part of b e to the j phi e to the j 10 t, or 10 was my omega. So that's going to give me, according to this, 0.0381 cosine 10t minus 112.5902 degrees, like that. All right, so that's our final answer here. Okay. All right. Now it's our final answer for the YP. It's not our final answer, right? We got to get the total solution. So total solution combines YP and YC, all right, which I've done here. I don't want to write in B and phi. I don't like writing numbers down. I like writing symbols because I'm less likely to make a mistake if I write down symbols rather than numbers, right? It's easy to transpose numbers. This is the general form of y sub c here, the two coefficients, the two unknown coefficients, C1 and C2. The problem is, so at this point, I know B and phi, but I don't know C1 and C2, and I got to solve for those, all right? So basically what I have here is 4 steps to be able to solving this. I have a step 3a and a step 3b, and there's going to be 2 more steps. So because I need 2 initial conditions. I need to get an initial condition on the first derivative. So I got to take the first derivative of this thing. So first derivative of y of t. So this is going to be minus, so I got to take the derivative of b cosine 10t plus phi. So that's going to be minus omega b sine omega t plus phi. All right, so notice, again, omega is equal to 10 here. So omega is 10. All right, and then I got to take the first derivative of C1 e to the S1t and C2 e to the S2t. So that becomes plus S1 C1 e to the S1t plus S2 C2 e to the S2t. And again, that can only be valid for t greater than or equal to 0. Okay, all right. Now what I got to do is I got to plug in my initial conditions. All right, so I have y of 0 is 0, and y prime of 0 is equal to minus 1. Let's just check. Is that what I said at the beginning? I think it is. Yes. Y of 0 is 0. Y prime of 0 is minus 1. Okay. All right. So what we got to do is we got to plug in my initial conditions. So here you can see the original equations. I'm going to write it like this. All right. This looks like it's the particular solution evaluated at 0 plus, let me just write it this, yp of t plus c1 e to the s1t plus c2 e to the s2t, right? So I'm going to write it like this, yp of 0 plus c1. Now if I plug in t equal to 0, e to the 0 is going to be 1, and e to the 0 is going to be 1. So I get that this expression simplifies to that, okay? Now, if you're talking about the derivative, right, y prime of t will be y particular of t derivative plus the characteristic or the complementary solution derivative. All right, so in this case, I'm just going to write that as y prime p of 0. That's the derivative of the particular solution. And then over here, we wrote down for ourselves what the transient solution's derivative was. Now notice, again, if I plug in t equal to 0, right? For t equal to 0, the exponential terms go to 1. So I'm going to get plus S1 C1 plus S2 C2 like that. So what that says is I can create a system of equations here, right, that is going to look like, let's just write it like this. It looks like I have y of 0 minus the particular solution of 0, right? So bringing this over to the other side. And y prime of 0 minus the first derivative of the particular solution evaluated at 0 equal to C1 plus C2. And this is equal to S1 C1 plus S plus S2 C2. This is true whether it's underdamped, overdamped, whatever, right? This is always going to be true. So this guy can be written as a system of equations here as 1, 1, S1, S2, all times C1, C2 equal to y of 0 minus yp of 0 and y prime of 0 minus yp prime of 0, like that. All right, and then I can just solve for C1 and C2 in MATLAB. All right, so basically, again, I defined 4 steps. What is the complete solution? I got to write it down with the unknowns in it. I got to compute the derivative with the unknowns in it. Got to plug in my initial conditions, and then I write a system of equations. All right, so here's what I did, right? I defined y of 0 as some variable, right? That's my initial condition. And y prime of 0 I defined as some variable minus 1. Now, what I have here is I've defined some system that I've written as A times C equals B, like that, where B is this vector here. Now, if you go back to my previous slide, I see I've written y of 0 minus b cosine. Notice what I've done here, right? This guy here is the particular solution evaluated at 0, okay? And this guy here is the derivative of it evaluated at 0, okay? And you'll see there should be a plus sign on this one because of the minus sign here. All right, so you'll see, if you walk through that slowly, you'll see why that has to be. All right, so I put so I defined my A matrix, and then I used inverse A times B, right? So I can say C equals inverse A, so A to the minus 1, that's the inverse, times B, like that. That's my C vector, my 2 unknowns. So this guy here is C1, this guy here is C2. And now, essentially what that means is that yc of t equals, if I want to write it this way, 0.6687 e to the negative 3t minus 0.6540 e to the minus t, all for t greater than or equal to 0. So that's our total solution. Here's how I go about plotting that in MATLAB. So notice what I did here is I defined for myself a time vector. Didn't talk about how I got it, but I basically said I came up with that time vector. Then what I have is this yp, right, which I did based on my b and phi values. Now notice, because my phi was in degrees, I multiplied it by pi over 180, okay? And then here is where I computed my y sub c. Now notice, because my c was basically it had 2 entries in it, so c was defined as a vector with 2 entries. And also previously in my code, I defined my S vector as the roots here. So that was a vector with 2 entries. What I did to write this, notice, is I said C of 1, the first entry in the C vector. So C of 1 is what I was calling C1. C of 2, the second entry in that vector, is what I've been calling C2. And S1, the first entry, the first root, was the first entry of that S vector I created, and S2 was the second entry of that S vector I created. So notice that code that I wrote there that sort of simplifies it a little bit and keeps it in terms of S and C. Again, I like keeping it in terms of those variables rather than hard coding numbers, right? Because then I can see much more clearly what's going on. Now, what I've done here is I plotted the particular solution, the transient solution, and the total solution all together. So hopefully you can see which one is which. The red one here, the red one is y sub c. The blue one is y sub p. All right, and the total is the sum of them. The important thing to remember, yp doesn't exist on its own. Yc doesn't exist on its own. In the real world, the total solution is what happens, okay? And you see that what happens is once we get into steady state out here, all right, and the transient is basically gone, what you see is that the steady state solution and the total solution become the same, okay? And in circuits 2, you make use of that all the time. All right, and you basically, in circuits 2, you forget that there's even a transient, and you just solve for the steady state solution. Okay? Doesn't mean there isn't a transient. Just means that, you know, most of the time we don't care about it. So what we do is we solve for the steady state solution only. If we needed to, we would just have to go back through this process.